Hello and welcome to Easy Simulation for Science and Statistics. I'm Dr. Mark Williamson for Transcend's Professional Development Core. This is a short video from the short video series. Let's get started. Big question on the front here. Why simulate in the first place? Why make up data instead of just using other data? Well, broadly speaking, data simulation is the act of creating data sets with known characteristics. And this can be used for a variety of purposes. And it's actually really nice because you can actually tailor fit data sets for what you're trying to do. Whether you're trying to learn things, learn new statistical methods. You're trying to teach those methods and you need specific data sets with specific properties. That's really helpful rather than trying to make one fit or go searching for one. It's also good for validation. Again, making sure your procedures worked, your models, your functions work. And then finally, it's really helpful for experimental design where you want to mock up or simulate a data set of what you think your study is going to generate. And so you can test things, maybe get a feel for what analyses you're going to do or sample size, etc. So being able to create your own data sets with specific characteristics through simulation can be very useful for science and statistics. So what actually goes under the hood? What are you actually doing when you're simulating data? So it depends on what you're doing, but let's just take a very representative example. And all these examples and the methods I'll be sharing will be in R, so it's R specific. But in R, in the stats package, there's this function called rnorm. It's a function that generates a vector, so a list, essentially of normally distributed random variables. And you have several inputs, most notably the vector length, so how many samples you want to generate, and then the mean and standard deviation from that normal distribution. So essentially, based on your mean, standard deviation, you're going to have some sort of normal distribution. And then when you run this, it's going to sample n amount of time. So if you do about 9 or 10, it's going to sample one here, then one here, one here, one here, one here, one here, so forth and so on, till eventually you have all your samples, and they should be drawn from that normal distribution with the mean and standard deviation that you gave. And of course, there's other distributions you can use. We'll see a couple of them, but broadly speaking, that's what's happening here. And so the data is nice because it will sort of be drawn from this distribution, but it won't be sort of exactly. So if you have a mean, of one, it's not like the mean of this subset is going to be exactly one, is going to fall within that distribution. So it's going to act like real data. So with that, let's go through some methods of actually simulating different data for potential analyses. So I'll try to go through maybe some of the most common tests, trying to simplify it down to the easiest way to do that. Some of these ones are a little more complicated, but I did my best to make them as simple as possible to get our feet wet here. So let's start with a t-test, which is going to be essentially comparing the means between two different groups. This is probably the easiest thing to simulate. And so I'll give examples in R, and then I'll kind of show you some graphs or tables to help make sure our data is simulated the way we think it is. Now, if you want this code, there's a link in the description to this video for a GitHub repository for this R code. So you can follow along, adapt it, use it, whatever you want. All right, for our t-test here, what I'm going to do is I'm going to create these vectors. I'm going to call them group A and group B because I say we want to look at the difference in means between these two different groups. We can run this function. We already looked at rnorm. So it's going to take an n. So let's just set that as 100. So we're going to have 100 samples, and we need a mean and standard deviation. So the first one, I'm going to have the mean of 0 and a standard deviation of 1, and group B is going to be mean of 1 and standard deviation of 1. So there's going to be some difference between them. Now I'm going to turn this into a data frame and then call it DS1, dataset 1. And so I'm going to have two variables in this data frame, group and value. So my value is just going to be getting those group A and group B, but then I need to actually have categories for this group. So I'm going to do something very simple. I'm going to repeat A, so for group A 100 times, so that for every value in this vector here, it's going to be labeled A, and then I'll do the same for B. Then what I can do is run a ggplot, a box plot to look at the differences between these groups. When we actually do that, this is what it looks like here. And that looks what we're looking for here. Now, since these are box plots, these middle bars, that's a medium, so it's not the mean, but we can see here that's going to be fairly close because it's normally distributed, but we see that the mean medium is somewhere in the range of 0 for group A, which is what we wanted. We drew from a distribution with a mean of 0 and a standard deviation of 1. And then our group B is around more the mean of 1, which we want. And we see the standard deviations look good. They look about the same because they should have the standard deviation of 1. So that seemed to work out fairly well. And of course, you could simulate any sort of group differences. You can make the standard deviation big or small. You can do more or less samples, have all sorts of different means. So this is really flexible. And then you can generate your own data here. Now, the next logical extension will be ANOVA, which is essentially like a t-test but with more groups. And so we'll piggyback off that with the code here. We already have groups A and B. Let's just create groups C and D, doing the same sort of thing with the RNOM function, 100 samples again. But for group C, let's make this a little bigger, a bigger mean, bigger standard deviation. Or group D, let's make the mean negative, but then keep a standard deviation of 1. So for my second data set, I'm going to do the same thing I did for the t-test, but just with 4 groups. So repeating A, B, C, and D 100 times, and then adding in those values for group A, B, C, and D. I'm going to do a box plot as well, and we'll see something very similar. Now, because the range of values are wider, just going to kind of zoom out more, but we can see A and B look the same. We got D here, which again, around the mean of -5, what we wanted, but with a standard deviation. So we see the spread of that box just about the same as A and B. But with C, we spread the standard deviation out so we can see that's very much extended what we want for. And so we could do this. Of course, if we wanted to do this is a one-way ANOVA, we could do a two-way ANOVA, we could do all sorts of things. And we'll see a little more complicated repeated measures ANOVA as well near to the end. All right, with that, so we had t-test ANOVA, which had a categorical variable and a numerical variable. Let's just go to all numerical variables with correlation. So this is going to be a little more complicated, but I'll try to walk through the logic. And I found this in the references. There's a great web page going through more correlation things. But so for this, what we're going to do is we're going to create variables. We're going to call rho, so that's like the correlation coefficient. So we're going to create 3 different ones. 0.6, which is a modest positive correlation, negative 0.9, which is a very strong negative correlation, and then a essentially almost 0 correlation, so it should be very essentially nothing. And then for our first x variable, should be more similar now. We're going to just do an RNorm, 100 entries here with a mean of 0, standard deviation of 1. So far, no different from what we've already seen. But now what we're going to do is we're going to have 3 other x variables that are going to be correlated with our x0 variable in different degrees. And so I found this formula from one of the references where essentially you have 2 parts and you add them together. The first one is your x0 variable multiplied by your rho, your correlation coefficient. And then you add that to this other thing here where you have the square root of 1 minus the rho squared times, then essentially just a value from a new distribution, whatever our norm of whatever mean standard deviation you want. And then so essentially, because you add these together, one part is going to be actually just part of each value from x0 plus sort of a new value. So it won't be identical, but it'll be correlated. You can do this for all 3 of them using the different rows that we already set up here. Of course, you could just add, this. You don't need to set a rho value. You could just put like 0 0.6, 0 0.6, 0 0.6, but this makes it a little easier to adapt. I'm going to create a data frame for this, and then I'm going to run a correlation plot to make sure the correlation that we're hoping for is actually showing up, and then plot it, scatter plots. Okay. So what we have here, correlation plot, we see with x0 and x1, it's 0.57. So yeah, that's very close to the 0.6 that we were hoping for. Again, this won't be perfect number here because it's drawn from a sample that should have that true correlation as 0.6, but it's a sample, so it's going to be somewhere in the ballpark. 1, 0, and 2 is 0.90, so almost exactly what we're looking for here. Now, this is interesting. X3 is 0.18 compared to the 0.05. So I guess just by chance, this had a higher correlation than what we expected. But if you ran this again with a different seed, it should be closer to 0 or the 0.05 that it drew from. And then if we can plot this, we really see the correlations that we're hoping for. So 0 and 1 is that moderate positive correlation, 0 and 2, strong negative correlation, and 0 and 3, which we're kind of hoping to set up as almost null, but this is a mild positive correlation because that correlation coefficient is 0.8, actually almost, or 0.18, almost 0.19. All right, so that's correlation, which you really don't really infer causality, as opposed to regression, where you're usually trying to you infer causality that like y predicts x, or sorry, x predicts y, rather than just looking at correlation. So obviously we could just do the same thing with correlation, but with regression models, you often can be more complicated, and in fact have categorical and numerical x variables for your y variable. So what I'm doing here is it's again a little more complicated, and I'm actually taking this from a way to simulate data, for example, of Simpson's paradox, but you can use this for more generally. So essentially what I'm doing here is I'm going to have different groups. So I'm going to have a grouping variable, which has 3 groups, 1, 2, and 3, and just like an x and a y variable. And so this is a little more complicated, but essentially what we're going to do is we're going to create a vector. We're going to call it mu. Essentially, this is the mean. Mu is a way of saying mean. And we're going to need 2 because we're going to have the x and the y variable, essentially, with different means. Then we're going to need a sigma, which is going to be a covariance matrix. It's going to have 2 things for each variable, a variance and a correlation. So the variance are going to be the values on the outside, where the correlation is going to be the values on the inside. You can set this up however you want. And then we're going to create as a data frame using actually not the R norm, but the MVR norm. It's like the multivariate, I think, normal distribution. And then you can put the mu in and the sigma, and it's going to generate this data, and we'll call it as groups. So 1, 2, and 3. And so I shift these around here. For this first one, the means were 0, then 2, then 3, so the means go up. And for the first one, the variance is set at kind of 2. This one, the variance is higher in one variable than the other. This one, it's lower. And for this one, it's kind of modestly negative correlation, then very slightly negative, and then in fact positive. So we can see all sorts of differences. And we're going to bind these together here to a data set. And then we can plot that with actually a scatter plot grouped by with colored and grouped with linear models by group. So what does it actually look like? So first of all, well, most of all, here we have it. And so we have the group colored by groups, and then the V2, V1, or Y and X, you could call it here. And it really does seem to have the properties that we're looking for. So for group 1, the means was supposed to be 0, so that's, yeah, looks like those means of the variables are around 0 here. We want that to be a negative correlation, so it's going down, and the variance is okay. Group 2, we have a lot higher variance with I believe the Y variable. So you see that's why those green dots are really spread out along the y-axis, and it's very slightly negative, less, the slope is less than group 1. And then for group 3, would actually be a positive correlation. So yeah, that slope is going up. As V1 increases, V2 increases, like we wanted with this positive correlation. So that is a way to sort of mix both categorical and numerical variables and have different groups with different characteristics. All right, let's switch over to repeated measures or repeated measures ANOVA. This is probably the most complicated, but again, we're going to be using different things we've already learned, as well as sort of tweaking things ad hoc. All right, so we've already seen this sort of stuff for the correlation, and we've already seen some of this group making and labeling from the ANOVA and t-test. So let's put that together. So first of all, I'm gonna now the difference between like a regular ANOVA and repeated measures ANOVA is that the idea is that each group is maybe across time, and they should be correlated because they're the same measurement, like maybe the same patient across different times, so they should be correlated. And so I'm going to create a row value that I'm going to say of 0.5 because he's being that's a good default. And so then what I'm going to do is I'm going to create 6 vectors, and they're going to be for 2 groups, so group 1, group 2, and then across 3 different time intervals, time 0, 1, and 2, to sort of simulate do groups measured across time. So for the time 0 for both the groups, I'm just going to do an R norm like we've seen before. One's going to have a mean of 150, one's going to have a mean of 100. Standard deviation the same at 20. But then as we go in, what we're going to do is we're going to correlate this. So for group 1, T1, we're going to have our row value times our previous value. And we're going to do just like we did with the correlation, the square root against the new R norm. And now because the square root of 1 minus rho times rho, that's larger than 0.05, like the rho. There's going to be more added here. And so actually, and if we do the same for T2, it's actually going to increase the overall mean that this is being drawn from, so the number should go up. So this can kind of simulate correlated repeat measures going up over time. Now, to sort of have a contrast for like group 2 that I don't want to increase, I'm simply changing this variable out to 1 minus rho. So essentially, because rho is 0.5, so this is half of the information, half the data is coming from T1, T0, T1, and then 1 minus rho is going to be 0.5, so half is from a new distribution. And so this should not go up. It should stay around the mean of 100 that we want. All right, I'm going to create a group, or a data set. So there's going to be a grouping variable, time variable, and measurement variable. And so going to have to be a little more complicated. So because we have group 1, so I'm going to call A, because we have 100 3 times, that's going to be 300. Same with B, but then I have to split it out more for time. So go by 0, 1, and 2 100 times each, and then to go to B, 0, 1, and 2 100 times. And then my measurements, all those 6 vectors. So I can plot it, summarize it, and also looks at some correlation. So if we look at the plot here, this is what we're kind of hoping to do here. We have group A, and we want to go up over time, so that looks pretty good. Turn around a mean of 150 that we set, and it keeps getting higher. And then, of course, these will be correlated, but we'll see that in correlation. It's hard to see on the graph itself. And then for group B, it's around 100. And we see here that, yes, indeed, it does not go over time. It stays here. But I think what's happening, you actually see the standard deviation kind of going down. I think because the more you do this, the less new information, the tighter the spread it is. So standard deviation actually goes down. And if we wanted to like correct for that, we'd have to do something more, like maybe boost up the standard deviation in each of the subsequent ones. But for here, now this is good enough. Now, again, if we have the summary, we can see what I kind of talked about here. For group A, the mean starts about 150 and it keeps going up, but the standard deviation remains constant. Whereas for B, we wanted the mean to be around 100 and it stays just around there, but the actual standard deviation definitely goes down to the when we get to the second time point, it actually looks like the standard deviation is almost half, which kind of sort of makes sense that we're losing variability each time, so it becomes tighter and tighter. All right, this is a big thing. We want to make sure they're correlated. So for looking at Group one, we see here for time 0 and time 1, yep, it's about 5. And then for 1 and 2, that looks like it's, yeah, about 5 or like, a little more. And actually group 0 and group 1 are correlated less, which makes kind of sense because if group 0 and 1 is correlated and 1 and 2 is correlated, 0 and 2 will be correlated to a lesser degree. And we see the same sort of thing for group 2, 0.65, 0.57. And then importantly, so if we look at group A time 2, group B time 2, the correlation is almost 0, which makes sense because those are drawn from distributions. They should not be correlated. So that is what we would expect as well. So that's a good confirmation. All right, finally, let's start out and switch to only sort of frequency data or like count data to end out here. So now we're going to use, instead of the R norm, we're going to use the R binomial. So we can draw from a binomial distribution. It has different inputs. It still has the number. So we'll have 100 samples each. But now we need probability and size. And now if we set size to 1, that means this is sort of like a coin flip. It'll only do 0 or 1. And that's what we want for sort of like count data. If we set the size higher, it would we could simulate things like dice roll. If we put size to 6, it would sample, or sorry, not dice roll. It'd sample multiple sort of binary events. So if we set the size to 2, it would be like 2 coin flips. But we just want count, so we'll do size 1, and then we can have the probability of. So a probability of 0.5 is they're equally likely for 0s and 1s. Probability 7.5, that increases the probability of 1 being found to like 3/4. Can create a data frame. So again, group and status. And we can create tables, sum it, and even do a plot, a stacked bar plot. So here's our actual data here that we generated here. And this is kind of what we would look for A, because there should be about a 50-50 split. 55 to 45, that's good. Essentially, it's not exactly 0.5 because this is drawn from a random distribution. So you can imagine if you did actual like coin flips, physical randomness, you could probably get something reasonably like this. And for B, because the probability is 0.75, we're getting it more like 3 times out of every 1, 0. 3 1s for every 0 about, and we can have our sum data set. We can create a bar plot to see them more clearly. Yeah, so group A, 50%, it's about 50-50 between 0 and 1. For B, it's mostly 1s and then a little bit of 0s. All right. With that, let's talk about some more complex horizons. I tried to create as simple ones for each of these main sort of tests. And obviously, I didn't run the ANOVA or t-test after that, but this is data you could use for that type of tests. Now, for more complex horizons, this is a great resource from Brad Duthie on creating simulated data sets in R. I took some of the information on simulating data with known correlations, but he has all sorts of things from simulating a full data set, different explorations of different distributions. So great resource here. And a more sophisticated one that I didn't get to, but the method looks a little more detailed, but very slick, and I think a little more sophisticated, from Thomas Ward, Simulating Correlated Data, where you sample these distributions from a multivariate normal distribution, you transform them, and then you transform them back, and you can essentially get really nice probability distributions that are correlated. So those will be in the references. So with that, thanks for joining me. I have the code available if you want in the description and all the references, including sort of the stats package, a little more on R norm and its other similar functions, how to do correlation plots, the Simpsons paradox simulation that I use for some of the correlation regression, and then of course those more complicated things, the simulating data and the simulating correlated data. With that, thanks for joining me. I will see you next time.